So I've got another polynomial for us to try graphing here. And with this one, we're just given the polynomial, right? And you're told, see what the graph of this thing looks like. So I want to continue to apply the techniques that we've been learning in this series of lectures, where we're looking at the roots, the multiplicity of the roots, and the end behavior, right? So to do that, we have to start by factoring this thing, and that's a rather largish polynomial, but we have tools for factoring, right? So I'm going to start thinking about the rational root theorem, right? And the rational root theorem tells me that my possible roots, let's see, the factors of the constant term, there's quite a few, plus or minus 1, 2, 3, 4, 5, 6. Okay, now I finally start skipping. Not 7 or 8 or 9, but 10 works. 11, 12, 13, 14, 15, 16. Now the next one I think is going to be 20. See, there comes a point where you can kind of start to refer back, right? 5 times 12 is 60. So then to get the next one, look down here at 4. 4 times 15 is 60. Then keep working your way down. 3 times 20 is 60. 2 times 30 is 60. And finally, 1 times 60 is 60. Now, really go to Excel or some other software package that you're familiar with and have it evaluate the polynomial at all of these numbers, because that's an awful lot of numbers. You're going to be here quite a while if you try to do that by hand. And if you do that, you will see that P of -3 is equal to 0, and P of 4 is equal to 0. All right, so that means x minus 3 is equal to 0, or x, x equals -3 or x equals 4 are the roots, which means x plus 3 and x minus 4, those are our two factors. Okay, good. So now, so far it's looking like x plus 3 times x minus 4, and there's going to have to be some quadratic in here. Whoops, didn't mean to change colors there. There's going to need to be some quadratic there that brings this up to 4th degree, the original degree here. Okay, so how can we find that? Well, we're out of rational roots. So our only recourse here is going to be long division or synthetic division, if you prefer. So let's see, if we multiply this out, this is x squared minus x minus 12. Double check that. So I'm going to divide this x squared minus x minus 12 into the original polynomial, x to the 4th, 3x cubed, minus 11, minus 53, minus 60, and this should go evenly. Right, so I'll do x squared, that's x to the 4th, minus x cubed, minus 12x, and we're going to subtract that, and we get, let's see, 4x cubed plus x squared minus 53x. So then I'll do a plus 4x up here, and that's looking good so far. 4x cubed minus 4x squared minus 48x, and then we're going to subtract. The x cubed go away. We get 5x squared. Let's see, 48 minus 53, that's 5 minus 5x, bring down the minus 60. I'll do plus 5 here, and that should work. 5x squared minus 5x minus 60, and when we subtract that, yes, awesome, we get 0. We came out even. Right, so then my factored version is going to be x plus 3 times x minus 4 times x, my pen's being a little weird here, squared plus 4x plus 5. Okay, so we're down to a quadratic polynomial there to factor for the very last part. That doesn't look to me like it factors, at least not into rational numbers. So let's get the quadratic formula out, and I get x equals -4 plus or minus the square root of 4 squared minus 4 times 1 times 5 over 2 times 1, and that's really where this is going to end. This is -4 plus or minus, this is 16 minus 20. That's the square root of -4 over 2, and we don't want, our goal is to graph this, right? So we don't want imaginary numbers, so I'm just going to leave that factor there, right? It doesn't give me any real solutions, doesn't give me any roots or x-intercepts. So my only two that I'm going to need to graph are these two, and if you look at the factored version here, the degree, the multiplicity of both of these is going to be 1. All right, so let's go to a graph, right? And so let's see, that was x equals -3 and x equals 4, and the multiplicity was 1 for both of them. And let's think about end behavior, right? We're looking at this x to the 4th term here. If I put a really big, huge positive number in there for x, I get an even bigger positive number, so that's going to be going up to the right. And if I put a really big negative number in there, I still get a really big positive number. So this is going to be going up to the left as well. All right, so let me get my roots in here. It's going to be -3, and over here 1, 2, 3, 4. And now I know what my graph is going to look like. It's going to come down. It's going to cut through here. Now, obviously, when we're sketching, this is not to scale. Where is the x-intercept, the y-intercept of this thing? Well, p of 0 is equal to -60. So the actual y-intercept, if I was drawing this to scale, would be way down here somewhere, right? But if you just keep that in mind, that all we're doing is sketching. We're just kind of trying to get the general shape of this thing, right? And it's going to look something like that. Now, I say something because it's not a super accurate graph, as it turns out, right? And I really want to emphasize the point that we are sketching at this point. There are a number of significant attributes of these graphs that we have not talked about how to find. They require calculus concepts like the first and second derivative. I had Excel graph this for me, and you can see it behaves very differently in here than you saw in my simple sketch, right? This has what we call an inflection point right around here. It's where the graph goes from being what we call concave up, and it kind of flips over in a sense and goes to being concave down, right? And then there's going to be another inflection point here where it goes back to concave up for the remainder of the graph. So, and that's fine, because we're not trying to be super accurate. If you wanted to be super accurate, we would do what I did here and go to Excel. All we're looking for is a quick sketch to get kind of a general idea of what the shape of the graph is going to look like. As you go further into your math education, you will learn more techniques, things like the first and second derivative test from calculus, that will let you refine the graph further and add these additional levels of detail. So speaking of calculus, this brings us to the end of our discussion of methods for sketching the graphs of polynomial functions. And it also brings us to the end of what really is the level of material that would customarily be covered in a pre-calculus class. Going into the next chapter, we're going to kind of transition up a little bit, and we're going to talk about approximation methods, ways that we can use polynomials to approximate other functions. There are a lot of advantages there. Polynomials, they only use 3 basic functions: multiplication, addition, and subtraction. Those are relatively easy for computers to do. So if we can come up with polynomials to approximate other functions, that's potentially a really powerful technique, a real processor cycle saving technique. So that's where we're going to be going in the next chapter, and at that point we're really going to be moving into more college level material.